So now we're going to be working with some proving and also simplifying of the series using the binomial theorem. And the basis of what we use for that is this expansion over here. So we use the expansion of 1 plus x to the power of n equals to nc0, x to the power of 0, and then x to the power of 1, so on, until ncn x to the power of n. And we use that basis to do some proving questions and then simplification questions as well. Okay, but you do have to keep that really well in your mind so you know what we're doing there. Let's start off with question 5 here. So firstly, just expand that. Yeah, so we know how to do that quite easily. We know that the first term will just be nc0, and since 1 to the power of anything is always 1, don't worry about it. Start off with x to the power of 0, x to the power of 1, x squared until x to the power of n. Now we want to prove that 2 to the power of n equals to nc0, nc1, nc2, so on. Okay? Now remember how I said we're going to be working with this. Yeah, so we're going to be using this expansion to prove and simplify. So firstly, let's have a look. To prove that 2 to the power of n using this, that means that here x has to equal to 1, right? Because you want 1 plus 1 to be 2 to the power of n. As well as when you have a look at this portion of the expansion, you can see that we have times x, x squared, so on. But over here, we don't have any x. So the only way to do that is if for this side, x equals to 1 as well. So that means by using this expansion and substituting in x equals to 1, right? I'm going to get 1 plus 1 to the power of n, which gives me 2n, as well as on this side, all the x's will just essentially disappear because it's just 1. So therefore, by substituting in x equals to 1, I've shown that 2 to the power of n equals to this series over here. Yeah? So can you see how it's quite simple, but you do need to recognize when you are given this question in an exam that you need to use this basic expansion up here. All right? So just know that with a lot of your proving questions and your simplify questions, you're going to be working with that basic expansion. All right, let's move on to 5c here. So here I want to prove that 0 equals to nc0 minus nc1 plus nc1, so on. So here you can see we're going plus minus, plus minus, plus minus, which should indicate to you straight away there's going to be a negative in there, right? So we're going to start off with our basic expansion of this, and let's consider our left-hand side. So for that to equal to 0, what does x have to equal? Yeah, exactly. X has to equal to negative 1, so you have 1 minus 1. Now, considering our expansion here, we're going plus, minus, and also it's negative 1 there. So you can kind of see that for this side, I also have to substitute in x equals to negative 1, right? So the x's disappear because it's 1, but it's going plus, minus. Okay, so let's substitute in x equals to negative 1. So we have 1 minus 1 to the power of n, that gives me 0. And over here, you can see this gives me the negative, but negative 1 squared remains as a positive. The next one will give me a negative as well, and then a positive, so on until I have negative 1n, which is exactly the same as that right-hand side there. So therefore, I just proved that 0 does indeed equal to that series. All right, so those were quite simple, I thought, but the main thing was you did need to recognize to use that. And then you just need to find out what do I need to substitute in to make the left-hand side equal to the right-hand side. Okay, so let's move on now to simplify questions. So those two questions we're proving, whereas here we want to use simplification. So question 5, to simplify this series over here, first of all, I want to consider our basic expansion of that, our basic expansion of 1 plus x to the power of n. And then I want to compare this expansion with that. And I can see that the difference is instead of x here and x squared, I have 2 and 2 squared. And finally, instead of xn, I have 2n then. So that indicates to me that I need to substitute in what? I need to substitute in x equals to 2, right? Because that's how I get that x squared to be 2 squared. So all you need to do now, just actually substitute in each of the 2's. So put that in there and then substitute 2 onto the right-hand side as well. So you have 1 plus 2 to the power of n, and that just becomes 3 to the power of n. So this whole series here can actually be simplified to just 3 to the power of n, yeah? So which you can actually, there's, no way of just doing that by looking at it, but we need to consider this basic expansion here. And we just think to ourselves, what do we need to substitute in so this resembles that? All right, great. So that was simplifying that. What about when we want to simplify this question? Here we have NC1 plus 2 NC2 plus 3 NC3, so on until n NCN. So notice that here we're going from 1, 2, 3, and then 4, so on till n. Yeah? So you can see that pattern forming there. Now I want you to consider your basic expansion of 1 plus x, n, okay? What do you get here? You get n C0, right? And then what do you get? You get nc1 of x to the power of 1. And then there'll be x to the power of 2 and x to the power of 3. Yeah, just not writing coefficients because I'm running out of space there. Can you see how you have that same pattern here? 1, 2, 3, 4, so on until n, which resembles the same as the coefficients here. So what does that make you think? If we have indices, which is 1, 2, 3, 4, and we have coefficients here, that's 1, 2, 3, 4, what am I going to do with my basic expansion so it looks like that? Just have a think there. So indices, 2 coefficients. What can I do so I will bring down that indice in front? No, I just gave it away, didn't I? So exactly, we need to differentiate it because somehow we need to bring down that index in front, like the coefficient. That's all we need to do. So now what I do is I differentiate both sides of our basic expansion. So differentiating this side, that constant just disappears. And this is just x to the power of 1, right? So that just disappears as well. So it's NC1. Bring down the 2, so it's 2 NC2. Bring down the 3 NC3, x squared, so on until here we're going to bring down that n. So you have n, NCn, and then x to the power of n minus 1 there. All right, now let's differentiate this side. So subtract 1, so n minus 1, and we bring down the n. Now, having a look at this, we see that we don't actually want the x there. So that means whenever we don't want the x there, is we just need to substitute in x equals to 1. So let's just substitute that in. So you just have that disappears, that x goes, and that just becomes 1 as well. So there's no point writing any of that. So you get NC1 plus 2 NC2, which looks exactly the same as that left-hand side, right? Good. And then finally here, we substitute in x equals to 1 as well. And that just becomes n times 2 to the power of n minus 1. So therefore, our simplified version of this series is just n times 2 to the power of n minus 1. All right? Great. So I think a lot of students with this question, their main concern is, well, how do I know I need to differentiate that there? Well, I hope you understand it's because we see that pattern here of 1, 2, 3, 4, so on. And once you see that pattern, it should kind of trigger in your memory of the x to the power of 1, x to the power of 2, x to the power of 3. And the only way you have of really bringing down those indices is by differentiating it, right? Because differentiation means that you do actually bring down that indice in front, and that's how you get the pattern of 1, 2, 3, so on. All right, cool. So that was question 5E. I want to now move on to question 5F here. So question E and F are very, very common in your exams. These are the kind of questions I love to give you. So we want to simplify 1 minus half in C1 plus 1 on 3 in C2 minus 1 on 4 in C3, so on. So 2 things you need to notice here. Firstly, instead of the coefficients being 1, 2, 3, 4, instead here you're getting 1 and then 1 on 2, 1 on 3, 1 on 4, right? So what's forming a pattern is actually just the denominators. Can you see how, well, here essentially I have 1 on 1. These denominators here are forming the same pattern, 1, 2, 3, 4, and so on. So what does that make you think? When we're considering we have x to the power of 1, x to the power of 2, x to the power of 3, how are you going to get those numbers on the denominator? So that's the first thing I want you to think about. Now, the second thing I want you to consider is the fact that it's plus minus, plus minus, plus minus. What does that mean for us as well? Okay, so there's 2 things that I want you to think about. So let's go back to that first thing I mentioned, which is instead of having the coefficients being in that pattern, what we have is the denominator of the coefficients being in that pattern of 1, 2, 3, 4, which means that should make you think about when we're considering the indices of what? Yeah, exactly. It's going to be integration in this case, right? Because when we integrate, that's how we'll move that to x0, add 1, divide by 1. Add 1, that becomes 2, divide by 2. Add 1, divide by 3, divide by 4. And that's how you get that pattern of the denominator on the bottom. Can you see that? Good. Now the next thing that's really important in integration is determining these values here. So how do I know it's 0 to negative 1? Well, that's where that second consideration I told you to think about came into play. So you could see that's plus minus, plus minus, plus minus, which means it has to be a negative in there, right? So when it's to the power of an odd number, it's going to be negative, and when it's the power of an even number, it's going to be positive. So that's how I know I want to integrate to negative 1 there. And why I want 0 here is because when I substitute it in, right, I just want 0 minus everything else. So it's not going to really touch that. Does that make sense? So I want this number to really not have any consideration at all. Now, before we go on, let's just have a look here what we've done. So we've worked out that we need to integrate it because it was the denominator that formed that pattern, and we worked out it had to be going to negative 1 because it's plus minus, plus minus. And we said to starting from 0 because we don't want it to affect the other numbers. All right? Okay, so let's integrate all of this now. So starting on this side, that x to the power of 0, that's just going to become x to the power of 1, which is just x. And since NC0 just equals to 1, that's why I write x there. Here, you add 1 to the index, so it's going to be x squared, right? And then divided by 2, so divide by the index. Plus 1, so that's going to be x squared, and then you divide by that. So on until here, when you have x to the power of n plus 1 over n plus 1, right? Okay, so now let's integrate over here. So we have 1 plus x to the power of n plus 1 over n plus 1 there. And now we just need to substitute in the numbers. So this is where you can see why I chose 0, because when you substitute in 0, this is 0, this is 0, this is 0. You get the idea. So it's all 0. Whereas over here, I'm going to be substituting in negative 1 there. Now, when I substitute in negative 1 squared, that becomes 1. Whereas when I substitute it into negative 1 cubed, that remains as negative 1 there, right? And then finally, that I just substituted in as negative 1. So you can see how that negative 1 is going to give us that plus minus pattern there, all right? Okay, then do the same on this side. So substituting in 0, that becomes 1. And substituting in -1, 1 minus 1, that will just become 0 on a number, which is 0 in itself. Okay, now finally, so this side just becomes 1 on n plus 1, which you can quite easily understand. Whereas this side, what we have is, since we have 0 minus this, right? So the first one becomes 1, whereas this, which used to be positive, becomes negative. So the positive plus negative just flips around essentially. And you can see here, what we've done is a really important step, which instead of having x to the power of n plus 1 here, -1 to the power of n plus 1, we've somehow made it -1 to the power of n. Now, how have we done that? So I want you to consider this. This negative here, right? That's just a -1, multiplying everything by -1. So this is essentially being multiplied by another -1, which means that that actually just becomes, because that's the power of 1, right? So you can add the indices together. So that actually becomes -1 n plus 2. And you can separate that, so it equals -1 to the power of n multiplied by -1 to the power of 2. Now, since -1 to the power of 2 equals to just 1, that's why that just equals to -1 to the power of n, like that. So that's how we've gone from negative times -1 of n plus 1 to -1 to the power of n there, which looks exactly the same as this, which we've just made it simplified to 1 on n plus 1 there. All right? Okay, so just a little bit revision. So what we've done here is just integrated that, and because it was just 0, that was just 0, right? And that negative flipped around all the signs. But the important thing was that over here, because we had -1 times -1, so become -1 n plus 2, which we could separate. That -1 squared is just 1, and that's how we changed it to -1 to the power of n, which looked the same as this, and this side equal to 1 on n plus 1. Okay, so very difficult question, I know, but maybe just have a look through it and you'll be able to get that.